Hi there and welcome to our C5 topic, how much? Quantitative chemistry, and today we're going to be looking at volume and concentration. Now volume should be simple-ish, but concentration we do a couple of calculations for that and it needs a bit of thinking about. Anyway, I'll see you at the end. Okay, so our objectives for volume and concentration is by the end of this lesson you should know and understand how to calculate the volume of a solution and how to calculate the concentration of a solution in two separate ways. Okay, now you're probably used to looking at volumes when you look at maths, but we're just going to look at a specific unit of volume that we use in chemistry. Now, if we take a centimetre line by a centimetre by a centimetre, we have 1 centimetre squared. Now the volume, if we go back another centimetre, is then 1 centimetre cubed, and this is one of the units that we use. Now the main standard unit for volume in chemistry is where we take 10 centimetres by 10 centimetres, and then by 10 again, and this is what we refer to as 1 decimetre. And because we've got 10 by 10 by 10, 1 decimetre cubed is equal to 1,000 centimetre cubed. Okay, now 1 decimetre is also the same as 1 litre. Concentration is a measure of how much of a chemical there is in a certain amount of volume. It can be measured in either grams per decimetre cubed or in moles per decimetre cubed. Now the concentration is dependent on the amount of solute that we can see here and here in red compared to the amount of volume that there is. Now you can see that we've got two identical volumes here, although this is in 2D, but here on this side we have it more concentrated because we've got more solute particles than we do on the other side, making this side here more dilute. Making dilutions is extremely important, and the reason being that for things like medicines, if they are too dilute, the medicine won't work. If it's too concentrated, it could cause an overdose or make you even more ill. Some solutions that you may use every day need to be diluted, such as orange cordial, and also milk for babies needs to be diluted to ensure that it's the correct concentration. Now, if we have a look at this table here, we can see how we can actually carry out dilution. So what we've got in this first column is the amount of the standard solution, that's 1 mole per decimetre cubed. Now if we put 1 with 9, we'll end up with 10 of a concentration of 0.1 moles per decimetre cubed. Now to get the same concentration but with a different volume, if we do 10 and 90 will give us 100, and then 100 and 900 will give us 1,000 centimetre cubed, or 1 litre, or 1 decimetre cubed. Now in order to calculate the concentration in moles per decimetre cubed, you can use this equation where concentration equals the amount of solute divided by the volume of the solvent. Now we often refer to this as C is the concentration, N is the amount of solute, and V is the volume of solvent. Now the units are moles per decimetre cubed for concentration, and then we've got moles, and then we've got decimeter cubed, and you can see that the units for concentration are exactly the same as the equation here. Now you'll need to be able to put this into a triangle so we can show how this will look. So we've got concentration is equal to the number of moles divided by the volume. Now GDA stands for your guideline daily amount, and you often have this on the food packaging and for different variety of foods, and this relates to concentration. Now I'm going to show you an example of a food label here, okay, and this is where you've got the vitamins and minerals that you have and how much you have in a 30-gram serving. So this could be, for instance, a packet of crisps or a bowl of a packet of cereal, and here you have your guideline daily allowance. So for example, if you had a 30-gram packet of crisps and there's 0.4 grams of salt, then that's 10%. Now what we can do is we can work out what our daily allowance is, and we can do this by multiplying the mass by the percentage. So if the mass is here, let's move that up a bit. If the mass here is 0.4, so we do 0.4 multiplied by 10%, and that's going to equal 4 grams is your daily allowance. Now food labels can be quite misleading. Now for example, a microwave meal could contain 2 grams of sodium. Now all of that sodium may have come from the salt, and 2 grams of sodium, we need to be able to know how much sodium that actually is. So what we can do is we can use an equation we've used previously, where we've got N, which is the number of moles, is equal to the mass divided by the molar mass. Now if a meal contains, let's say, 2 grams of sodium, then we can work out what the mass or the number of moles is. So if we have N is equal to 2 over 23, and our number of moles is equal to 0.087. Okay, now what we then need to do is to work out the mass of the salt. So we rearrange this equation here because we want this as our answer. So we have M is equal to N times MR. So N is 0.087 multiplied by, now this is our mass for sodium chloride, so that's NaCl, which is 58.5, so that's 35.5 plus 23, and that will equal 5.09 grams. Now if on the meal that's how much salt there is, and if we saw in the previous slide that our daily guideline allowance, or guideline daily allowance, is 4 grams of salt, then we're quite significantly over the top of our daily allowance. Okay, so we have finished the looking at volume and concentration. Now we need to remember that there are 1,000 centimetre cubes in a decimetre. We also need to know how to calculate the concentration in grams per decimetre and also in moles per decimetre, using the amount of substance divided by the volume, and that has to be in decimetre cubes, so you need to remember to convert that into decimetres from centimetre cubes, which is what we normally use. Anyway, I hope you've enjoyed it, and I will see you again soon. Bye bye.